And now for our last section in this class, we're going to talk about the analysis of variance, also known for short as ANOVA. And we get the ANOVA from analysis of variance. But first up, we have to talk about something called the F distribution. The F distribution is very similar to chi-square in that it is not symmetric and skewed to the right. Also, all the values of the F distribution are non-negative. 0 or a positive numbers are acceptable. But different from chi-square, F depends on 2 different degrees of freedom, not just 1. So we'll have 1 for a numerator and 1 for a denominator in order to get the F distribution. Ultimately, though, we're going to be using our analysis tool pack, clicking on that one factor ANOVA, and getting a p-value back that we can compare to our alpha. So one-way analysis of variance, or one-factor analysis of variance, is used to test the hypothesis that 3 or more population means are all equal. One-way ANOVA is used with data categorized with one factor or one treatment. So there's one characteristic used to separate the sample data into those different categories. So our null and our alternative hypotheses are pretty much consistent. Our null hypothesis is that all the means are equal, and our alternative hypothesis is at least one mean is different from the others. We use the word treatment because early applications of ANOVA involved agricultural experiments where different plots of farmland were treated with different fertilizers or seeds or insecticides, etc. Some assumptions for ANOVA: normally or approximately normally distributed data. The samples are, of course, randomly selected, but the populations from which the samples were obtained must be normally or approximately normally distributed. Samples must be independent, and we're going to assume the variances of the populations are equal. We've got a little bit of liberty here with those variances of populations. It turns out that we can have them off by a little bit, and we can still run an ANOVA pretty successfully. Next up, I'm going to talk about some nitty-gritty, but we're not going to be calculating these test statistics. Again, we're going to use technology to get us the test statistic or the p-value, but I do want you to know where this stuff is coming from. So we've got 2 different estimates for the population variance. One is called between group variance, and the second is within group variance. The idea is if there are no differences in the means, this test statistic will be close to 1. The between group variance and the within group variance will be approximately equal. But when they differ significantly, the between group variance will be much larger. And so we would have that test statistic being much larger than 1, and we would end up rejecting the null hypothesis. And as mentioned before, this is a pretty complicated calculation to make. Even though we've got variances here, we're talking about 3 or more populations that we would have to calculate. So again, we're not going to worry about that calculation. We're going to use technology. I've provided 2 additional videos on how to set up your spreadsheet with the correct tool pack. One for Excel and the data analysis tool pack add-on, and one for Google for the Excel minor analysis tool pack add-on. So if you're looking for those, check out the description in the video, which will point to those other 2 videos. And some more information, we have between group variance is sometimes called the mean square. The numerator of the formula to compute the mean square is sometimes called the sum of squares between groups. And we've also got the sum of squares within groups when we're talking about the within group variance. So, reminders. A small p-value leads to rejection of the null hypothesis. A larger p-value, we would fail to reject the null. So remember, we're always comparing the p-value to alpha. So if our p-value is smaller than alpha, we reject the null. If the p-value is greater than alpha, we do not reject the null. These are exactly the same conditions that we've talked about for every hypothesis test that we've done. So we're going to focus on, once we get that p-value, what does that mean? So here's a sample display from Excel. we have 3 columns, so we have 3 populations. They give us the counts for each one, so the n values for each one, and then some more information, the average and the variance for each one of these populations. And do notice that the variances aren't quite equal. Remember, this is sample data, sample variance, not population variance and population means. And then down here in the bottom, this is our Anova calculation that Excel does. It gives us a lot of things to look at, particularly things to point out. The big one is the p-value here. It gives us the p-value, and this is what we'll want to compare to alpha. And then the other 2 pieces of information that we could use if we wanted to do a traditional method test instead of a p-value method test. This F here is our test statistic, or our test value. And this F crit, this is our critical value. So if I were to draw an F graph, my critical value 3.07309 would give me a rejection region to the right. ANOVAs are right-tailed tests. And then my test statistic is 4.0711. And since my test statistic is in the rejection region, for whatever this display is giving me, this would lead to a rejection of the null hypothesis. Notice that that is pretty similar to our p-value up here being 0.01951. That's going to be less than alpha. And even though I don't have alpha represented here, alpha is what you have to input in Excel or Google, so that's how it gets the critical value. I'm pretty sure this alpha is 0.05. But for the display, the p-value is really the only thing that we need to pull from all of this information. So let's see how we can use it. I'm grabbing this example from a book by Triola. Does exposure to lead affect IQ scores of children? So there was an environmental health study involving children living within 4 miles of an ore smelter in El Paso, Texas. And this is used to melt ore to separate metals. And the smelter emitted lead pollution. There was a concern that the children might be affected by this. So they gave the students IQ tests and test the lead levels in their blood and came up with some data. And the data here represented in the table. So these numbers are indicating IQ scores from this IQ test. And it's questionable whether IQ is really a good representation of intelligence in general. It is a biased test, just like many of our standardized tests are. But it does give us one measure to see if higher levels of lead might be different from lower levels of lead in this performance of the test. If we do some statistics for these groups, we've got the sample size n, our average, and our standard deviation. We've got approximately normal distributions. There's an outlier potentially in the low blood level, but the thing that we really want to focus in on are these averages. And we do indeed see that the low blood lead level is higher than the medium and the high blood lead levels. But we can't make a decision just by looking at these numbers, because 102 compared to 94, how close is it? We can't really make that judgment just on our own understanding. We need to use some statistics. So that's exactly what we'll do. So we'll start out checking assumptions, and we form our hypotheses. For our null hypothesis, our population means are all equal. Our alternative, at least one mean is different from the others. And so since I have instructions in Excel here on your worksheet, I'm going to look at doing this in Google and also Excel so we can see both of them. Okay, now that we have our hypotheses, it's time to enter our data. I'm going to show you how to do this both in Excel and in Google. In Excel, I have the data listed low lead level. There were quite a few more of those children compared to medium and high lead level. So I want to make sure that my sample data are all collected in the same column or the same row. I've done it here by columns, so we have all of the low lead in one column, all of the medium in the second, all of the high in the third. Now, in order to do an analysis of variance, we click on Data, and we come over here to our Data Analysis tab. If you don't have the Data Analysis tool pack installed, go check out my demo on how to do that. We'll click on Data Analysis, and we're going to go all the way up to the top for Anova Single Factor. So the only thing that's separating these three groups is the level of lead in their blood. So Anova Single Factor, first up is the input range. This is where we want our data. So we can select our data, and we don't want to stop here. We want to go all the way down. So make sure we collect all of the data. The extra blanks are not a problem for Excel. So we have all of our data selected. It's grouped by columns because we had each of our samples in the columns. If we had it by rows, we would select rows. I did not select the labels in the first row, so I don't want to select that. Alpha is 0.05, that's perfectly acceptable alpha, so we'll leave it like that. And actually what I am going to do is I am going to change this. I am going to select those labels, and you'll see why I select them. So labels in the first row, all I did was change the 2 to a 1, so I went up to the top and grabbed those labels. In the output, it just puts those labels in instead of column 1, column 2, and column 3. So it might be a little more convenient to select our labels. And then output range, I usually like this in the same table, in the same spreadsheet as my data. So I select one cell, that's all you need to do, and then you click OK. It does some calculation and it gives us our output. Also, something interesting to note, this is exactly the same Excel display that we already dissected earlier, but still, it gives us some good information. Our p-value is 0.019, and we're comparing that to an alpha of 0.05. And so we would reject the null in this case. If we reject the null, we would say there is enough evidence that one population average is different. Though we could assume it's likely the low lead group, that is an assumption, and we would need to do more to break down and determine, yes, it is the low level group. So all we can say from an ANOVA test is that one is different. We cannot identify directly that a particular one is different. Now I'm going to take my data and transfer it over to Google, and I'm going to run the exact same test in Google just to see the difference. So for Google, we'll go up to add-ons, and for add-ons, we want this XL Minor Analysis Tool Pack. Again, if you don't have this tool pack installed, please go see my video on how to install it in Google Sheets. We'll click Start. It brings up our display window, our selection window, and we're going to click on Single Factor ANOVA. Notice that we have almost exactly the same options here that we had in Excel. So we have our input range. I'm going to grab our data. It's grouped by columns, and we have our labels in the first row. Alpha is 0.05, and for the output range, I'm going to come back up here to the top and select one next to my data, and then click OK. And now check this out. We get the same information in a very similarly laid out table. So that's pretty nice that we have very similar results between Google and Excel. What makes this so nice is that if you can do it in Excel, you can do it in Google, and vice versa. So learning one does not limit you to that one. You can do it in both. So how is the p-value related to the test statistic? The larger values of the test statistic result in smaller p-values. Anova test is right-tailed. And so some graphics to represent that. If we have a small test statistic and a large p-value, our test statistic is going to be in the non-rejection region. But if we have a large test statistic and a small p-value, our test statistic is going to land in the rejection region. Why not just test 2 samples at a time? Well, Chapter 9 gives us a t-test for 2 population means, but when we throw in a third one, we actually increase the risk of a type 1 error. So instead of doing Anova, if we were to try to pair them off and test them 2 at a time, we're doing 3 different hypothesis tests. And as we do 3 different hypothesis tests, we're actually increasing a type 1 error, even though our significance level of 0.05 might be the same for each of them. Say it's 0.05. Because we're doing 3 different ones though, the type 1 error compounds. And so we use one test for several different means instead of doing several tests with pairwise comparisons. In the next part of our lesson, we'll look at 2 more examples where we would use Anova to see if we have equal means.